Hey guys, welcome to my presentation. My name is Vishnu Gokul Krishnamurthy, and my topic is design and modeling of quadcopter control system to maintain a constant altitude. And the presentation style is AIAA style. Let's go to the next slide. Hey guys, this is my research schedule. These are the things I did sequentially, and I was a little bit on and off some target dates. And let's go to next slide. Okay, here is my abstract. The goal is to design a drone flight control system which maintains a constant altitude. I use the method of using simulink here, and we are just customizing an existing control system which is available in the aerospace block set of MATLAB. And the style which I'm going to use is a model-based design. And what it does is after simulation, it just does a C code which gets auto-coded into the flight so that the drone can just maintain a constant altitude. Okay, these are the sensors we are going to use in the drone. Those are ultrasound, which measures the distance from the ground using the time travel of sound waves. And second is a camera, which determines the horizontal motion, and the pressure sensor determines the altitude of the drone. And we have IMU, which determines the acceleration and the angular rotation here. Okay, here we are for the drone type and the build. This is just a basic X-type quadcopter, which is just a 4 BLDC motors. Thrust, roll, pitch, and yaw commands can be given independently. The system is under-actuated, which is the 4 actuators are for 6 degrees of freedoms. Those are 3 translational and 3 rotational. Okay, this is the motor mixing algorithm here. In order for the drone to hover, we need to give some thrust. For thrust, we need to just give all 4 thrust commands to the all 4 motors here. And for rolling, we need to increase or decrease the left right pass. And for pitching, we need to increase or decrease the front and back pass. And for yaw, we need to increase or decrease the diagonal pass here. Okay, this is the overview of the control problem. Here are the 4 actuators, which are the 4 motors, which injects the force and torque to the drone to manipulate all the 4 motors exactly so the drone can hover. And the sensors here, the ultrasound camera, the pressure, and the IMU, these helps us directly or indirectly to estimate the state of the drone. And the system states includes either angular position, altitude, or horizontal velocity. And the software runs in the algorithm that takes in our set point and estimated state to calculate the precise motor commands that will inject necessary force and torques to the motor here that forms the controller. Okay, this is the flight control architecture, which goes into the flight code of the flight control system. So here we have the 6 PID controllers, 4 in the inner loop and 2 in the outer loop. These 4 are for thrust, yaw, pitch, and roll. All 4 can be connected and manipulated independently. And these 2 are for roll and pitch, which are supposed to be in the position controller. This position controller makes sure that the drone stays in the same position by giving the reference as origin. And we also have some estimated yaw so that the drone can rotate from his body frame to the world frame of reference. And we are giving the yaw signal as 0 degrees here to maintain the drone without rotating in any point. And this gives the quick walkthrough of the flight control architecture. And this is the flight controller part designed in Simulink, which is just the Simulink representation of the flight control architecture. The flight code has several other components along with the flight control software. Each has its own separate code and firmware. It includes memory management, sensor interface, battery management, internal messaging, motor interference, and LEDs, and Bluetooth interference. Okay, here are the 2 methods to load the flight code on a drone. The first method is gonna be like we need to write the C code in hand and we need to make some changes and we can compile the C code into a binary file. Later we can load that file into the drone firmware. But there are some drawbacks in the first option because we cannot tune all the PID controllers here and it is difficult for us to explain all the process. And so that is the reason we are just choosing the second one. It is nothing but a Simulink model we are going to build first and which generates C code by itself. And the C code is compiled to the binary file. Later it is transferred to the drone using a Bluetooth. These are the components inside the flight control system. The first one is a state estimator, which is nothing but a logic that needs to convert all the measured states from all the sensors to the control state read by the controller. Example, let's say if the drone has a air pressure sensor, but here we are not trying to control the drone to any particular pressure. So all we need is just altitude. So we can just convert this air pressure to the altitude here. And there's a fall protection. The second thing, which is it's a logic that determines whether to set the certain flag or not, which is nothing but if the drone rotation rate is more than a fixed threshold, or example, if the altitude or the position of the drone is certain outside the boundary conditions we set, then there's a case that the drone might run out of control. So there's a shutdown flag to prevent this from happening. And the third thing is a data logging, which is nothing but a black box used in the flights. It just has a .m file and which can be downloaded into MATLAB after the flight to see the results of the drone flight and everything. Here we are trying to design a simulink model that takes external commands and the measured sensor readings as inputs and outputs the commanded motor speeds and the shutdown flags for the safety of the mini drone that will shut down the mini drone when the flag is set. This is the stock model of the control system designed in Simulink. This is nothing but a classical feedback control system. Here the command is nothing but a system that generates reference signals for the drone to follow. And the FCS is the flight control system. Here the aerodrome generator, and it also houses all the 6 PID controllers here. And the flight load block is auto-coded into C code and it is loaded into the drone here. And this output from the flight control system or the force and the torques, which are injected into the airframe, which is nothing but the drone itself. And we also have a visualization block, which plots signals and runs the 3D visualization. We'll see later. And this environmental block has the things to model gravity or air pressure for the plant and sensors. And these sensors over here simulates noise and dynamics of the force sensors on the drone. We are making some changes in the flight control system as we are not needing some of the parts. Here we can see the three inputs here, and I'm removing the third input, which is meant for precision landing. We are not here following the precision landing because we are just going to make sure the drone maintains a constant altitude above the ground. For precision landing, they use the camera and image processing, so we are not going to need that. So I just remove the input here. In the same way, we can remove all other things which are not necessary for this part. It is the inside the components of the flight control system. These are all the four parts I mentioned earlier: the state estimator, and the data logging, and the shutdown flag, which is the fall protection here, and the flight controller. All these constitutes the flight control system here. Inside the state estimator, two steps are involved in taking the raw sensor measurements and generating estimated states. First, we process the measurements and then we blend them with the filters to estimate the controller states. We don't want any precision landing here, and the reference signals, we are just hard coding the values in the block because the reference command of the block isn't the part of the auto code and it is not going to be loaded into the drone itself. So we are just hard coding it for 0, 0, minus 0.7. So which gives the drone's position, which is zero point 0.7 meters above the ground. The minus sign is here because in the z-axis is down the drone reference frame, so the altitude will be zero point 0.7 meters up. We are building this control system using the approach called model-based design. Here the flight control system has all the control system software, and this code has to interface with all the rest of the drone firmware. It has two inputs, which are the raw sensor readings and the reference commands, and it has two outputs, which are the stop flag and the motor speeds. These two commands are given as inputs to the model here. This represents everything apart from the flight control software. So it takes two inputs here and it gives outputs as sensor measurements. So this model wraps around the flight control system and provides us a feedback loop. And there are two types of model we are using in this drone here. The linear model, which is a low fidelity model for determining the controller structure in gains. The other one is a non-linear model, which has high fidelity and it's used for simulating the results and verifying the system. For this model-based design, we are using certain steps. The first one is to create a high-fidelity model, which is nothing but a nonlinear model, and we need to verify that it matches the realities using certain test conditions. And the next step will be We need to create the linear version of it once it reflects the reality. Now we will be having two different models. One is linear and non-linear. So we can use the linear model and linear analysis tools to design and analyze the control system. And we can use the non-linear model to verify the performance of the control system. And here the model is not just a single block, it also has certain things like actuator, airframe, environment, and sensors. So all these together considers as a model here, and all these four have their own model-based design. We are using a variant subsystem approach, which means we have the option to choose between two models, which act as a switch. One is a linear, other one is a non-linear. Here we are using the non-linear airframe, and while tuning the PID controllers, we'll be using the linear airframe. This is inside the nonlinear model. The left block is the AC model, which contains the actuator models and the model of how environmental disturbances impact the system. Simply, the forces and torques are calculated inside here, and these forces and torque are fed to the 6 degree of freedom model. This 6 degree of freedom model is a rigid body model that comes with the aerospace block set. This is an existing model. Since we are using this is a perfect example that we do not need to write any new equations for the motion of rigid body. We need to determine the parameters for like mass and inertia by ourselves here. This is inside the environment model. It also uses the variant subsystem approach. It has two models, which is the constant environmental variables. The other one is variable environmental variables. We are using a constant one here because the air pressure, density, and everything is constant since we are just a little bit above the ground. This is the inside view of a sensor model. It has two things. One is the dynamic sensor with noise. Other one is a feed-through sensor. We are using a dynamic sensors here, and inside that is a hard-coded sensor calibration which goes into the sensor block. This sensor block has all the components like ultrasound, camera, IMU, and pressure sensor over here. After designing the control system using all the non-linearities, there's a simulation for the quadcopter which is flying zero point 0.7 meters above the ground. You can see it from here. And I just wanted to perform some safe failure test where I just inside the 6 degrees of freedom block, like I just changed the gyro bias to 3 times its own value so that to see what happens. After changing the gyro bias, as you can see, the drone just started to hover at first, and then it moves away slightly, and it starts to lose its position, and eventually it will crash. We are going to linearize the model by following some steps. Although the nonlinear model is more accurate and reflects the reality exactly, we need a linear system to tune the PID controllers in our architecture. So we need to linearize both the flight software and the models in the system. The flight software is difficult to linearize as it has if statements, switches, and state machines. So we need to create a new control design model that can be easily linearizable, and we need to tune all the 6 PID controllers for that. Here first we are going to tune the altitude PID. So we can adjust the altitude without affecting the roll, pitch, and yaw. We need to linearize the altitude loop and adjust the gains so that we can get the desired performance. To make it simple, I just removed some sensor blocks on the stock model. And for the altitude loop inside the flight control subsystem, I just grabbed the altitude controller and the mixer motor algorithm and the thrust motor command block and connected that to all the top level and just removed rest of the flight control software, maintaining that roll, pitch, and yaw to be 0 here. Here inside the altitude controller loop, a PID controller is added first and it is changed to PD. This will set the gains to the current value, and we just remove the existing PD gains here, Now the altitude reference in the PD controller is compared to the true altitude. The error is fed to the PD controller, and then a feed-forward gravity term is added to the PD controller, which gives the positive or negative thrust for the drone to move up and down. For linearizing, we need to open the PD block and then we have to click the tune. The control loop gets linearizes, and from the plant in the tuner, we can see the model. It will also show the state space matrices of the plant we are dealing with. In the PID Tuner app, we can adjust the response time and the transient behavior of the loop by adjusting the sliders, which is positioned above. And to find any certain frequency domain performance, we just set the bandwidth to 5 radians per second and the phase margin to 60 degrees. This gave us a p-value of 0.32 and d-value of 0.3. After we applied the P and D gains to the controller, we had a problem that the drone was not lifting from the ground. And I just tried to scale the scaling factor for 10%. We didn't make any changes. It was trying to lift. And I just increased the scaling factor to 20% and added the same PND gains here. And after that, the drone started to hover the same before. Here I just tuned only the altitude controller. In the same way, we can tune all the 6 PID controllers. We can tune yaw by keeping the pitch and roll constant by holding the altitude fixed. Then we can consequently tune roll and then the pitch in the same way. Once the 4 controllers in the outer loop is tuned, we can move to the other 2 in the inner loop. Yeah, from this project, I have learned something important. To design a good model, we need just a model-based design. It serves as a good foundation here. And to create a good model, the time spent is more than to create an actual control law. And there's some possible modeling problems which may include the ultrasound because it may be working at low altitudes or aerodynamics change when flying close to the ground or some variations in the hardware. We can fix the issue by system identification and other physical tests. My future work will be I will plan to design a control system for resting drones. These futuristic drones have the capability to attach themselves to a nearby wall or the ground using some gripper kind of mechanism. When attached, these motors stop spinning so that they can save some power. And these are the references which I used for my project and I have mentioned all here. Thank you everyone for patiently listening to this, and I would like to thank Dr. Elliot for approving this video presentation. And you can shoot me your questions to my email or you can just post in the feedback form. Thank you.